All right, good morning, everybody. This is Mr. Ainsworth. We're going to get into curve sketching here in Section 6 and take a look at a variety of different functions here and do some detailed graphing. And go ahead and take a look at it and browse through this page 1 here as you like. And it's basically a summary of how do you find the zeros, how to find the asymptotes, both horizontal and vertical, as well as oblique, how to find your x and y intercepts. And what do you do with the first derivative test? What do you do with the second derivative test? And so on. So it's just a summary of everything we've learned so far. Go ahead and read through that. But basically what we want to do is for each function here, analyze and sketch the function using the following. We're going to be taking a look at the domain to find the vertical asymptotes, abbreviated VA. We're going to find out any holes if they have any, and find their exact coordinates. We're going to use the first derivative to find our critical points. We're going to use the second derivative to find any points of inflection. And we're going to check the end behavior to find any horizontal asymptotes. We're going to find x and y intercepts if we can. And if the degree of the numerator is exactly 1 greater than the denominator, we're going to find some oblique asymptotes too if the function has them. So let's get right into it. Let's take a look at our first example here. And take a look at y equals negative 1/3 times the quantity x cubed minus 3x plus 2. And go through the certain steps here and analyze everything first, and then after that do some detailed graphing of everything we know. Okay, first of all, it's a polynomial, and the domain for all polynomials is that it's always defined on the set of reals. So the domain D is a set of all reals, and because it's all reals, we don't have any vertical asymptotes. So the domain is set all reals, and that tells me no vertical asymptotes. Okay, polynomials never have vertical asymptotes, by the way. Only rational functions have those, points where they're undefined. Polynomials don't have any holes either, so none for polynomials. And so what we want to do is find the critical numbers to find the relative extrema. Okay, the first derivative test is to find the critical numbers, and these are used to find relative extrema. I'm talking about the relative max and min. Okay? And also we determine where the function is increasing and decreasing. We use the first derivative test for that. So we need to calculate a derivative. Alright, and to do that, the very first thing I need to do is distribute through the negative 1/3 there to see what's going on. So I'm going to do that. So f of x is going to be equal to negative 1/3 x cubed plus negative 1/3 times 3 is 1, so plus x minus 2/3. So just distribute through the negative 1/3 through the function. Remember, here's the function right up here, and then take a derivative. So let's go for it. F prime is equal to negative x squared plus 1. Here's our first derivative. Now from that I can find some critical points to help me find the relative extrema and figure out where the function is increasing and decreasing. So from this I solve it. I get x squared is equal to 1 by shifting it over. You take the square root and you get plus or minus 1. Okay, so those are the critical points. And what we need to do is the first derivative test on that to figure out where the function's increasing and decreasing to see if we have a relative min and max. So let's do that. Let's do a first derivative test here. Here's negative 1, here's 1. Excuse me, 1. Let me fix that. Okay, and let's test it. And get your eyes focused in on f prime here. Okay, so take a number like negative 2 and evaluate the first derivative at negative 2. So f prime of negative 2, that's going to be negative of negative 2 squared plus 1. It's going to be negative 4 plus 1, which is less than 0 is negative, which means it's decreasing there. DEC for decreasing. And pick a number between negative 1 and 1, like 0. So f prime of 0. It's going to be 0 plus 1, or 1. That's positive. Positive means that it's increasing in this region here. INC for increasing, or you just use an increasing line. So right away I see that we have a relative min at negative 1 because it goes down and then back up. So negative 1 comma something is going to give us a relative minimum here in a minute. Okay, and then pick a number to the right of 1, let's call it 2, so f prime of 2, and that's going to give us the same value of negative as negative 2, so that's going to be negative 4 plus 1 is negative 3, and that's negative, of course, so negative means that it's going back down, it's decreasing on that interval from 1 to positive infinity, and over here is negative infinity. So right away I can already tell that we have a relative minimum here, and we have a max here, because the function goes from positive or increasing to decreasing, so we have a max at 1 and a relative min at negative 1. So let's go ahead and just summarize that. So min at negative 1 comma something, max at 1 comma something. Now whatever you're trying to find the y values, you just substitute them back into the function. And when you do that, you just go ahead and substitute it into your original function up here and get your y value. So when you substitute negative 1 in, you're going to do the arithmetic and you're going to find out that you get f of 1 is going to be equal to 0. And then f of negative 1, you're going to get negative 4/3 when you do the arithmetic. Okay? And again, you just substitute in the original function to get those y values. Okay, now we need to see if we have inflection points too, so we need to take the second derivative for that. So let's evaluate f double prime, and the second derivative is negative 2x, and you set that equal to 0 to find your inflection points. And so we have only one possible inflection point there, and because x is 0 is another critical value. But we don't know if that's going to be an IP or not. All right, you have to check for a change in concavity. So you do a second derivative analysis on 0. So you pick a number to the left of 0 and to the right of 0. So that's easy to do. F double prime of negative 1. And again, get your eyes right here on your second derivative and do a second derivative test. So F double prime of negative 1 is negative 2 times negative 1, and that's obviously 2, and that's positive. And if it's positive, it's concave up here on that interval from negative infinity to 0. But what happens on 0 to infinity? You got to pick a value like 2 and to the right of that. So you evaluate the second derivative at 2, and you get negative 2 times 2, or negative 4, and that's negative, which means it's concave down on that interval. So we have a change in concavity here. So this is an inflection point at 0 comma something. So you substitute that into the original function here, and f of 0 is negative 2/3. So you have an inflection point at 0 comma negative 2/3. Okay, so that's a major result. So we've got, we know the relative min and max. We know the inflection point. Let's check in behavior here. Polynomials don't have horizontal asymptotes, because when you take the limit to infinity, you get infinity, which is not a real number. So just remember, polynomials don't have horizontal asymptotes, and they don't have vertical asymptotes. So polys do not have any horizontal asymptotes, nor vertical asymptotes, polynomials. Okay, only rational functions have those type of things. Okay, and the last thing what we need to do is find x and y intercepts. So an x-intercept is when y is 0, so x comma 0, and a y-intercept, oops, there we go, is found when you let x equal 0 and you find y. Okay, so if you substitute 0 in for x, you're going to get, when x equals 0, you're going to get y is equal to negative 2/3. So that's a y-intercept. Okay, 0 comma negative 2/3 is your y-intercept here. Just doing algebra 1 right there. And when you find your x-intercepts, you let y equal 0, and you have to solve 0 equals negative 1/3 times x cubed minus 3x plus 2 equals 0. Okay, and you're going to have fun solving that equation because that's a cubic. And you're going to have to remember your synthetic division for your cubics to get your your zeros there. So when I multiply by negative 3 on both sides, what you really have to solve is 0 equals x cubed minus 3x plus 2. And use synthetic division on that. Synthetic division, use your rational root theorem. Okay, so when you do that, you're going to be looking at your coefficients. Let me see, the coefficients P and Q. P comes from the factors of 2, and then Q factors of the lead coefficient there, which in this case is 1. And you want to look for possible factors, P over Q. In this case, 2 divided by 1. So possible factors are plus or minus 2 divided by plus or minus 1. And so your factors are, factors of 2 are also 1, so plus or minus 1. So when you get that, you have plus or minus 1 and plus or minus 2 as the possible factors of the polynomial. And you test each one by one until you end up with a 0. So you guys remember that. It's called synthetic division. So when you do your synthetic division, you test 1 or negative 1, you're not going to get a 0. But when you test negative 2 and use your coefficients here, we have 1, and then let me see, there's no x squared term, so there's a 0 there, and then negative 3, and then a 2. And do your synthetic division, you get 1. Negative 2 times 1 is negative 2. Add, you get negative 2. Multiply, you get 4. Add, you get 1. Multiply, you get negative 2. Add, you get 0. Oh, there's a 0 there. So what's happening here on this one is that we have an x squared minus 2x plus 1. That's equal to 0. That's quadratic, and that's x minus 1 quantity squared equals 0, which means your 0 is, we have another 0 at 1. Our 0 here is at negative 2, and the 0 down here is at 1. So we have two zeros. Okay? So we have two x-intercepts now. We have one at 1, and we have one at negative 2. So our x-intercepts here are at 1 comma 0 and at negative 2 comma 0. So we're going to use those to help plot. So you're going to have to do your homework on these problems and remember all your Algebra 2 skills in order to do some detailed sketching. Okay, so the first thing, you want to plot all the points that we have here, and then we use our concavity to help us graph the function, and also use our first derivative sign analysis to help us. So let's plot the points here. We got a 1 comma 0 is here. That's going to be an x-intercept, so the graph of the function has to go through that. Negative 2 comma 0 is over here. It has to go through that point. We have relative min. Let me see, relative min at negative 1 comma negative 1 1/3. Negative 1 comma negative 1 1/3 is about right here. That's a min. And then we have a max at 1 comma 0. So here's a max, a relative max. Okay, and now we use our concavity. Use the concavity to help graph. Okay, f of x. So let's take a look at what happens to the left of negative 2. Is it concave up or concave down there? So let's look at that. So concavity test. Here we go. It's right here. We need to do another concavity test, and what happens? Oh, okay. Well, to the left of 0. No, it's right here. So everybody, eyes right here. Concavity. Okay, so to the left of 0, it says concave up, and to the right of 0, it says concave down. Okay, so let's go to our graph. To the left of 0, it's concave up, and it has to go through their x-intercepts here. And we know it's a cubic, so it's got to be concave up here. So through here, it's got to be concave up. Oh, by the way, we have a y-intercept too. Let me find it. Where is the y-intercept? 0 comma something. 0 comma negative 2/3. That's right here. So there's your y-intercept there. So let me see if I graph that right. And yes, so the graph has got to be. Oh, let me see. And where's my inflection point too? My inflection point 0 negative 30. Okay, so 0. So the inflection point here at 0, -3, or excuse me, 0, -2/3. That's an inflection point. That's where it changes concavity. Okay, so to the right of it's concave down, and to the left of it is concave up. See, right here in the concavity test right here in second derivative. So knowing what I know about inflection points and knowing what I know about concavity, I know that to the left of 0, it's concave up, so it's got to be looking like this here. Concave up. It's got to do those 2 points. Now at 0, -2/3 is an inflection point, which means it changes concavity from up to down. So f, the function here, f of x, has to look like that in green. It has to go through my points in red. And notice it has a max at 1, 0, so it's a high point, so it's got to hit that and bounce back down. And then it's got to go through the minimum, and since minimums are low points, it's got to hit that and bounce back up and go through that x-intercept. Now, you ask yourself, how do you draw it, after the max, And if you want to do a little bit better detailed graphing, then you plot, let's say, 3, something. Find out what the function is at 3, or find out what the function is at 2, and you can plot more points. So you can plot more points, okay, to be more accurate, if you like. All right, to the left of -2 and to the right of 1, okay? But that's basically a good sketch because I've labeled the inflection point. Again, it's in red right here. I labeled the max, I labeled the min, I labeled the x-intercepts, and I used my concavity to help me graph. And that's what you're expected to do on all these problems. To give a good accurate sketch and graph all relative extrema and inflection points and use your concavity to help you. Okay. Moving on, let's try another one. Let's try a rational function and do the same thing. Okay. We have y equals x cubed divided by x squared minus 4. This is a rational function. Now, rational functions potentially have vertical asymptotes, horizontal asymptotes, and oblique asymptotes. So you have to investigate on each one what you have and what you don't have. So when you look at the domain, you look at the denominator here for the domain. And that can never be equal to 0. So the domain on this one is when x squared minus 4 cannot be equal to 0. So when is x squared minus 4 not equal to 0? It's when x squared is not equal to 4. That means x cannot be equal to plus or minus 2. So it's all reals except plus or minus 2. And these become vertical asymptotes because there's no way you can remove them. They're non-removable discontinuities. Non-removable discontinuities. And because of that, they become vertical asymptotes as opposed to holes. Okay? If you cannot factor and simplify, you don't have any holes. Okay? So to find holes, you got to factor and simplify. And if you can do that, you got some holes. But in this case, there are none. Okay, now what you do is you find the first derivative. Okay, f prime to find the critical points. So let's do that. Let's use the quotient rule. So we have y prime is going to be equal to, we have x squared minus 4 times the derivative of x cubed, which is 3x squared, minus x cubed times the derivative of x squared minus 4, which is 2x, all divided by x minus 4 to the second power. Okay. Okay, so when you distribute through and simplify here, you're going to get, what are you going to get? 3x to the 4th minus 12 x squared minus 2x to the 4th, all divided by x squared minus 4 quantity squared. And you simplify that, you just get x to the fourth minus 12x squared, all divided by the denominator. Okay, now this is your first derivative. What you want to do is you want to factor that, and to find your critical points, you got to factor that and set equal to 0, and look where it's undefined. Already, I'm looking at the denominator. I know we have critical points at plus or minus 2. So we have critical points there. So critical points at x equals plus or minus 2, looking at right here. And then also I need to set the denominator or the numerator equal to 0, because you set y prime equal to 0. All right, f prime equal to 0 to find the critical points all the time. So I got to set my numerator, this right here, equal to 0 and solve that, because the fraction is equal to 0 when the numerator is equal to 0. So I got to solve x to the fourth minus 12x squared equal to 0. Well, factoring out x squared, I get x squared times the quantity x squared minus 12 equal to 0. And that means that x squared equals 0 or x equals 0. And then here I got x squared equals 12, and I take the square root, I get plus or minus 2 root 3. So I've got 3 critical values there, and I've got 2 more over here. I got 5 critical points, and I've got to do a sign analysis on that to figure out relative extrema if I have any. Okay, so this is going to be fun. So let's do a first derivative sign analysis on this. So this is 0 here. And then I got to plot 2 and negative 2. So here's 2, over here is negative 2. And then 2 root 3. 2 times root 3 is 3.4, so it's over here. 2 root 3, and then negative 2 root 3 over here. So I've got 1, 2, 3, 4, 5, 6 regions to test. Fun. So negative infinity over here, positive infinity over here. So I'm going to have to do some testing here. So here we go. We're going to have to make some more room on this. So here we go. Let's do some analysis. Here we got f prime of something to the left of negative 2 root 3. Now, root 3 is 1.7, and 2 times 1.7 is 3.4. So to the left of negative 3.4 is like negative 4. So I need to test negative 4 in the first derivative. Okay, now when you do all your tests, you just substitute it into your derivative, all right, and test the sign. Now I know the denominator is going to be positive all the time, so the only thing you have to check is the numerator and see if that's positive or negative, because you're always going to divide it by positive. So really I have to check this numerator here. So I can take negative 4 to the fourth power minus 12 times negative 4 to the second power. Okay, and this negative 4 to the fourth, that's going to be 16 times 16. That's 256 minus 12 times 16. And that's going to turn out to be positive. So that's going to be positive. That's increasing in that interval. And then you got to pick something in between negative 3.4 and negative 2, and something like negative 3. So f prime of negative 3, test that, you're going to end up with something positive. Okay, so you do all your tests and do your arithmetic on the side, and you can verify my results. You're going to get it's going to be negative there. All right, and if it's negative, that means it's decreasing in that interval. And then you pick something in between 0 and negative 2, like negative 1, f prime of negative 1. You substitute it into the function, you get 1 minus 12 times 1, and that's negative. All right, and so since that's negative, it's decreasing in that interval too. And if you substitute 1 in there, it's going to be also decreasing or negative. So f prime of 1 is also going to be negative. And if you pick something like 3 in between 2 and 2 root 3, you get f prime of 3. And that's going to be the same thing as negative, 3. Let's evaluate that. Let's see. Well, that's going to be the same as negative 3, so it's going to be negative as well. And then something beyond 3.4, like 4, so f prime of 4, that's going to be the same thing as negative 4. It's going to be positive, so it's going to be positive over here in this region from 2 root 3 to infinity. So I'm looking for change in sign. So at negative 2 root 3, it goes from increasing to decreasing. So that tells me that I have a max here at negative 2 root 3, and nowhere else in between here there's a change in sign, But over here from to the left of 2 root 3, it goes from decreasing to increasing, and that tells me I have a min. So if it goes down then back up, you got to have a minimum. So I do have some relative extrema at negative 2 root 3 and then at 2 root 3. I have some relative extrema. I got to find those values. And I also have to check the second derivative too to figure out if I have any flexion points. So what I need to do now is I need to find the exact extrema, and to do that I have to evaluate the function at 2 root 3 and at negative 2, 3 and see what happens. Which means I have to substitute back into the original function here to find the extrema. So use the original function to find extrema. Okay, so I need to find f of negative 2 root 3. I substitute into the function there. And when you evaluate it and simplify it, you're going to get negative 3 root 3. You can do the arithmetic there. And when you substitute into the positive 2 root 3, positive 2 root 3, and you simplify it and see what you get 3 root 3. So I found my extrema here. I have a max at negative 2 root 3, comma negative 3 root 3, and a minimum at 2 root 3, comma 3 root 3. So I got my extrema here. I can use that to help me graph too as well. Okay, now I have to find possible inflection points. So I have to take this derivative, the first derivative here. Let me highlight it here. The first derivative, this is f prime, and I have to differentiate it and get my second derivative. And, oh boy, it's going to be fun. So here we go. So y prime is going to be equal to x to the fourth minus 12x squared all divided by x squared minus 4 to the second. Okay, now I have to differentiate it. So here we go. So y double prime is going to be, and this is a quotient rule, y double prime here. Take x squared minus 4 to the second times the derivative of x to the fourth minus 12x squared, which is, it's going to be 4x cubed minus 24x minus x to the fourth minus 12x squared times the derivative of the denominator. Now I have to use the chain rule. Let me get some more room here. Hang on for a second. Okay, now chain rule on the denominator here. So I go 2 times, I'm going to need some more room, 2 times the quantity of x squared minus 4 times the derivative of the inside function, which is 2x. All right, and then divided by the denominator squared. So that's to the fourth power. Okay, now check this out. Look what's in common. I see that, and that in common. What we're going to do is we're going to factor out one of those binomials in the numerator and cancel out with the denominator. So in essence, what's going to happen is that all the powers are going to be reduced by 1. That's going to change to a 1. That's going to be canceled out to 1. And this fourth power is going to change to a third power. And what you're going to get is y double prime is going to be equal to x squared minus 4 to the first power times 4x cubed minus 24x minus x to the fourth minus 12x squared times 4x there, all divided by x squared minus 4 to the third power. Okay, and then what you have to do is you got to simplify that. So you got to multiply your binomials, and you have to simplify that numerator. And when you do, you get all said and done, you're going to get 8x cubed plus 96x all divided by your denominator. You can verify that and go through it in detail. And you got to set this equal to 0 to find your inflection points. Okay, now remember, a fraction is only equal to 0 when the numerator is equal to 0. So what you have to do is you have to solve 8x cubed plus 96x equal to 0. And look at the denominator here too for any critical points. So critical points are 2 and negative 2. And here, if I factor out an 8x here, I get x squared plus, let me see, 12x there. Oh no, just 12. 0. So x could be 0 here, and then when x squared equals negative 12, that's not real. Okay, so there aren't any more possible critical points. So we're just at 0 and plus or minus 2. So your possible inflection points are x equals 0 and plus or minus 2, because you have to look here, and then you also have to look here in the numerator. So you got to test for a change on concavity. So what you have to do now is take your second derivative, which is here, and you have to do a concavity test. So check concavity. So we need to do f double prime. We got here's 0, here's 2, and here's negative 2, and you got to use second derivative to check concavity. All right, so you need to pick some points to the left of 2, negative 2, and between those values. So you got 4 places to check. And when you check that, you got to check the second derivative. All right, so we've got to check f double prime at negative 3, f double prime at negative 3. And once again, we're using the second derivative here. When you evaluate the second derivative at negative 3, you should probably, there's all kinds of ways. You can use this function here, this second derivative here, or you can factor the numerator. Let me write it down here. You can factor it. This might be easier to use as 8x times x squared plus 12 all divided by x squared minus 4 quantity cubed. Use this derivative here and check concavity. Might use the factored form because it's easier. Okay, so when you substitute negative 3 here, I got a negative here. 8 times 3 is negative. And then this is positive. So I've got a negative times a positive. All right, all divided by what? Well, let me see. Negative 3 squared is 9. 9 minus 4 is 5. 5 is positive. Well, this is going to be less than 0, so it's going to be negative there. So it's a negative in this interval from negative infinity to negative 2. And that means it's concave down. Okay. Then what you want to do is pick something between negative 2 and 0. So like negative 1. So f prime of negative 1, do a sign analysis. So right here, 8 times negative 1 is negative. And then negative 1 squared is 1 plus 12 is positive. So negative times a positive. All divided by what? Well, negative 1 squared is 1. 1 minus 4 is negative. Negative cubed is negative. So now I see a double negative there. This thing is positive. So it's positive in this interval, which means it's concave up. And again, this is a second derivative concavity check here. And then you plug in 1. So f double prime at 1. And you do the same thing. 8 times 1 is positive. So positive times. And then here this is positive. All divided by 1 squared minus 4 is negative. Cubed is negative. So that's negative. So that implies that it's concave down. And then you pick a number bigger than 2, like 3. And you try that. And then f double prime at 3. Okay, so you go 3 times 8 is 24 positive. Times 3 squared plus 12 is positive. Divided by 3 squared is 9 minus 4 is 5. 5 cubed is positive. Divided by positive. Well, that whole thing is positive. So then if it's positive, it's got to be concave from 2 to infinity. So we're going to use that to help us graph. Okay? Okay. And then what we want to do is we want to find any x and y intercepts. So I know that when x is 0 here, I put 0 in, right here and right here. I get 0 divided by 0 minus 4, and that's 0. So when x is 0, y is 0. So I know it goes to the origin. Okay, so a y-intercept at 0, 0, and also the x-intercept is 0, 0. Because if you set y equal to 0, then you're gonna get x equals 0 as well. So the x and y intercepts are both the origin. Okay, it doesn't intersect the axes at any other point. That's what I'm trying to say. And now what you want to do is plot all the extrema. You want to plot all the extrema and use the concavity to help you graph. And plot all the axes or the asymptotes. So let's review. We've got vertical asymptotes at plus or minus 2. So that's what I do first. I want to graph those. So we have a vertical asymptote here at x equals 2. We have another vertical asymptote at x equals negative 2. We know it goes to the origin right here, so that's a point that it goes through. We have any extrema, and we do have some extrema, so we have to evaluate those in a minute. But we also notice here that the degree of the denominator is 3 and the degree of the denominator is 2, so it's exactly 1 greater. So what we have is we do have an oblique asymptote, okay? We don't have a horizontal asymptote because the degree is higher in the numerator than the denominator. So right here, no horizontal asymptotes, but we have an oblique, okay? And we have to use some, because this has been satisfied right here, the numerator is exactly 1 degree higher than the denominator, and we have to do some long division to find our oblique. So that's going to be fun. We'll do that in a minute. Okay, so now what we have to do is find the oblique asymptotes. Because when the degree of the numerator, 3, is exactly 1 greater than the degree of the denominator, 2 here, you have obliques. And the way you find oblique asymptotes is through long division. So I need to take x cubed divided by x squared minus 4, and that's completely easy. So long division, I take x cubed divided by x squared minus 4. So the very first thing is I take x cubed divided by x squared, which is x. Let me erase that and then start over again. I need more room. So I take x cubed and divided by x squared minus 4. So x cubed divided by x squared is x. That's first step is divide. First term divided by first term. And then I take x times the binomial x squared minus 4. And that gives me x cubed minus 4x. And then third step is you subtract. X cubed minus x cubed is 0. And then 0 minus a negative x 4x would be positive 4x. So here's my remainder, 4x. So what do I have? Since that's positive, I go plus, and then 4x divided by x squared minus 4. And so my oblique asymptote is this linear portion here. It's always a linear portion because oblique asymptotes are lines. It has to be linear. So oblique asymptote, OA for short. VA for vertical asymptotes, OA for oblique asymptotes, and HA for horizontal asymptotes is y equals x. Okay? So I need to plot that as well. So here we go. Y equals x here. Okay, so I have my oblique plotted. I have my 2 verticals plotted. I don't have any horizontals because the limit to infinity, the limit to infinity of the function here, as x goes to infinity is infinity, so I don't have any horizontals. And let's see, we're about ready to begin. So here we go. I need to plot the relative extrema. Now, a relative extrema, I need some decimal for these values here. I need to know exactly where negative 2 root 3, comma, negative 3 root 3 is. So let me see, 2 times 1.7 is about 3.14. So this right here is negative 3.4 roughly, and 3 times 1.7 is about negative 5.1, so negative 5.1. So left 3.4 and then down 5.1. So left 3.14, Yeah. So let me see, there's -3, and then -3.4, and then down 5.1. So 2, 4, right about there. Okay, that's going to be, that right there happens to be my max. That's relative max. So let me label it max right here. So max. I also know it's asymptotic to this line y equals x, and to the vertical line x equals -2. And looking at the concavity test, I know to the left of -2 it's concave down. So I know right away, just by using that it's got to go through this point here. It's got to be asymptotic here and here. And it's got to go through my max, which happens to be at -2√3, comma, -3√3. There's my relative max. I know it's concave down there, and it's asymptotic to the oblique and the vertical. So I use my concavity test right here to kind of help me graph this function from -infinity to -2 in that interval. Now between -2 and +2, it's concave up, and then from 0 to 2 it's concave down, so I have an inflection point here at 0, 0. Because when x is 0, y is 0. So this is an inflection point at the origin here. So it's concave up to the left of it and concave down to the right of it. And I'm using these asymptotes here. So I know it's asymptotic to x equals -2. And it's got to go through the end. And not only that, it's concave up right there. Notice it's concave up. And then it switches concavity to concave down. So here on the left of 0, it's concave up. On the right of 0, it's concave down. And if you're wondering if it's possible to cross an oblique asymptote or horizontal asymptote, the answer is yes, it is. You just can't cross vertical asymptotes because it's where the function is undefined. And then what's happening to the right of 2? In the concavity test here, it says that it's concave up to the right of 2. And so I know that. And I have a relative minimum at 2√3, 3√3. And so that's at +3.4, 5.1. So I go right 3.4, up 5.1. So right 3.4, up 5.1, right about there maybe. Right there, that is a relative min at 2√3, 3√3. And again, it's about 3.4, 5.1. You can verify that with a calculator if you want. So, and it's a relative min, which means it's a low point. And it's asymptotic to the vertical line and then asymptotic to the oblique. And it's concave up on the interval from 2 to infinity. So I know it has to look like this. Okay, and there's a sketch of the function there. It's an accurate sketch. You can verify it with the graphing calculator. Okay, your TI-83 384 or whatever you're using. Okay? All right, and that's what's expected for you guys. You guys are going to have to do a lot of work using first and second derivatives to find your inflection points and find your relative extrema, and then use your knowledge of the domain. Go ahead and that will determine the vertical asymptotes. If looking at the degrees, you'll be able to find the oblique asymptotes and the horizontal asymptotes, which in this case it didn't have any. And using the original function, you're able to find the y values for the extrema. Okay? All right, and I know this is, I might have been going a little bit fast, but this is a video. You can pause me and fast forward me and remind me anytime you want and review the lesson as you go. Okay? We're going to call this part 1 of the video here. I'm going to stop here, and then in part 2, I'm going to do examples 3 and 4. So try your homework tonight, give it your best shot, and come prepared tomorrow.